Okay, thank you very much. We're here for the last module of Module 1, that is Module 1.3. Remember, I told you we divided our class Module 1 into 1.1, 1.2, and 1.3. And here we're going to look at chemical potential. We're not going to go deep because this is just the first stage of the physical chemistry class. That is a 300 level. And I know that biochemistry students are here, so we'll just talk about chemical potential, introductory aspect of chemical potential. Okay, and we'll follow this outline: introduction, definition of chemical potential of solutions, and we'll conclude. Chemical potential, represented as mu, is the change in Gibbs free energy per mole of any substance in the system. If we have a pure substance or a system of constant chemical composition, that is a closed system, the change in Gibbs free energy is given as equation 1, the G equal to V dP minus S dt. Of course, it's the same, we can turn it. The G equal to minus S dt plus V dP, still the same thing. Now let us consider a homogeneous phase called a solution, in which there are different substances or components, species I to J, such that Ni and Nj represent species I and J respectively. Consequently, the species are Ni1, N2, 1, 2, 3, up to Nj are constant. The Gibbs free energy of the phase depends only on temperature and pressure, in which the variable composition is related as given below for an open system. Now, the total differential of that equation will be what we have down there. We differentiate with respect to P, we differentiate with respect to T, we differentiate with respect, at the first time with respect to P, we'll keep T, N1, N2 up to Nj constant. We differentiate with respect to T, we'll keep P, N1, N2, Nj constant. We differentiate with respect to N1 and also differentiate with respect to N2. Now, when we now simplify that equation, we'll have equation 4. You can see the summation sign, which tells us that we are summing, all the Ni, N1, N2, N3, and so on. Now, from equation 4, under isothermal condition and isobaric condition, the T equal to 0, the P equal to 0, we'll have the G, means that we have at constant T, PT, and Nj, we'll get equation 5, where the G over the Ny, that is the partial differential of free energy against partial differential of Ni, gives us what we call the chemical potential of the system. Of course, chemical potential is a driving force for chemical reaction. It prompts the tendency of a substance to diffuse from one phase into another. It is also a kind of chemical pressure, and it is an intensive thermodynamic function. Therefore, chemical potential in terms of Gibbs free energy is given by equation 7. The G is equal to S dt plus V dP, which we already know. So we're adding that chemical potential term, summation of mu I d and I. That's what that means. Of course, for solutions, if we consider a migration between two phases, phase alpha and beta, we're saying the same thing. Look at equation 8. The G is equal to mu1 alpha minus mu I beta minus mu I alpha bracket D and I. That's what it means. So if the G is 0, then it means that the chemical potential in the two phases must be equal. Mu I alpha must be equal to mu I beta. And that's what equation 9 is telling us. Then we can also use chemical potential to predict the spontaneity of chemical systems, just like we did with Gibbs free energy and the equilibrium constant. If the change in chemical potential is greater than 0, it's non-spontaneous process. If it is equals to 0, it's equilibrium and reversible process. And if it is less than 0, it is a spontaneous process. Now, just like we define chemical potential in terms of G, we can also define in terms of E, H, and A, that is internal energy, enthalpy, and Helmholtz free energy, respectively. So you can see that as equation 10, 11, and 12. All the equations we know before are there, except that we're now adding the chemical potential term, which therefore means that the chemical potential, change in Gibbs free energy, Ni, change in internal energy, change partial differential of enthalpy, partial differential of Helmholtz free energy. This is a very short one. We looked at chemical potential in terms of thermodynamic parameters and also chemical potential of solution. So that brings us to the end of module 1. So the next class we'll look at module 2, starting with module 2.1. Thank you very much, and I hope you enjoyed the class. See you in the next module.